So this is the second part of the fluid video, or sorry, fluid notes. So we're going to continue on with some more practice with the buoyancy equation. So here we have a balloon, and we want to figure out what is the volume needed to actually raise up this load. So pause the video, work on this yourself, and we'll go over it in a second. All right, so once again, what we have to do is basically just set up the whole sum of the forces. Now, one thing that I know I always have trouble with whenever it comes to buoyancy of usually something like this, of like a balloon, the one thing I always forget is I forget to include the weight of the gas. In this case, the weight of helium. This is going to make sure you want to make sure that you include it. Now again, there's a diagram here, so that kind of hints that you're supposed, or tells you that you need to figure out the weight of the helium, but you don't always have this diagram. So you want to make sure that you practice getting the diagram yourself and you don't forget it. So I set up the same thing. Once again, I want this buoyant force to be able to counterbalance the two weights, the weight of the helium and the weight of the load. Now, this is where you want to make sure that you're paying attention to your subscripts. So the weight of the load's easy. That's just mass times gravity. We know what the mass is, so that's fine. But the weight of the helium is a little bit different. It's going to be, well, we don't know what the mass is. Instead, what we actually have to do is we have to go back to what I said before about liquids and replace mass of the helium with rho v, density of the helium times volume. Now note that there are two densities. The density of air for the buoyant force, because that's the fluid that's being displaced, and this is the density of the material, the helium, the gas that's displacing the air. This comes up a lot where you're going to have to, where you have multiple densities, and you have to be aware of which density goes in for buoyancy and which density goes in for the object. All right. Since I'm looking for V, what I want to do is I want to bring this to the other side. So there's a G on both sides, so I can just drop them. And then I subtract the rho V here over to here. There's a V on both, so I can pull it out. And now I just need to get the volume by itself, so I can divide the density over to here, plug my numbers in, end up getting that the volume is going to be 160 meters cubed. All right. Now, using buoyancy to solve the most famous problem, the crown problem. So here we have a crown, and we need to figure out, is it gold? Note that gold has a specific gravity of 19.3. So pause the video, work on it yourself. We'll go over it in a second. All right. Now, the way we're going to do this is a little bit different, mainly because they tell me what the specific gravity of gold is. I want to actually figure out what this crown's specific gravity is. All right. So in here, we know that the weight, from part B, we know that the scale reading, which is the force being pulled up plus the buoyant force, is going to be equal to the weight pulling it down. Now, if I move the buoyant force to the other side, and we end up, or actually not the buoyant force, I guess the two weights to the other side, we end up getting this. The difference between the regular weight and the altered weight is equal to the buoyant force. Well, that makes sense. So that's going to be equal to rho Vg. Now we know that the crown's weight can actually be defined as rho Vg as well, where rho is the density of the crown. So we can take these two terms, again, because specific gravity is the density of the object divided by the density of water. I can do the same thing. I could take this term, divide it by this term. I take this term and divide it by this term to get this. So again, like I said, this telling me that I'm looking for specific gravity hints that I want to find a way to rewrite density of the object to density of the fluid. So I end up getting this relationship. Now, weight is just mass times gravity, so that means all the gravities in these three terms can drop out. So what I get is that the specific gravity of the crown is equal to the crown's mass divided by the difference in the masses, this mass and the apparent mass. So plugging the numbers in, I end up getting that the specific gravity is 11.3. Now, if you look in the table in the textbook, that's lead. So this crown is actually made of lead, not gold. So this is the famous buoyancy problem where, for those who didn't know, Archimedes was tasked with figuring out whether or not a crown was made of gold. And because the crown was awkwardly shaped, it was hard to figure out what the density actually was because they couldn't find a way of finding the volume. And the whole story goes is that it fell in the bathtub and he realized that the water rose, so the amount of the volume that the crown had displaced an equal volume of water. So you're able to use that to figure out what the density of the crown was. Now here's an interesting side note. I said before that any material that flows that doesn't have a fixed shape is a fluid. So that means air is a fluid. And we're in the air, meaning that we're displacing a fluid. So the question is there a buoyant force on us? Well, yeah. Turns out that there is a buoyant force on us. So we could do the same calculations to figure out, well, what is the buoyant force on us? We'll take an average person, 70 kilograms. We're going to assume that we have a density roughly about water, and we have a volume of about 0.07 meters cubed. Using these numbers, we get that the buoyant force on us is 0.2 pounds. This means that we are actually 0.2 pounds heavier than what our bathroom scale reads. So every time you weigh yourself in the bathroom, just remember you're technically 0.2 pounds fatter than what that scale reads. All right, so going back to this, the whole buoyant force. Well, if the buoyant force is greater than the weight of the object, then the object is going to accelerate upwards. That just comes from Newton's second law. And it's going to do that until it reaches a point where the buoyant force is equal to the weight of the object. So that means that we end up getting a situation like this, that rho vg of the fluid is equal to rho vg of the material, or rho v equals rho v, since the value of g is the same. So this gives us a really cool way of figuring out whether or not how much an object will float when it's submerged in water. So let's practice an example where we have a lock. Now, wood has a specific gravity of 0.6, and let's just say that it has a volume of 2 meters cubed. Well, the mass of the log is about 1,200 kilograms. We use the specific gravity to find the density and its volume, and we get that's what its mass is. Now we know that the mass of fluid, of an equal volume of fluid, ends up being 2,000 kilograms. So this means that if I fully submerge the log in the water, the buoyant force coming from the water is actually going to be higher than the weight of pulling it down, meaning it's going to actually float up, which makes sense. You submerge something in water, it'll lift up. So it's going to float. But now the question is, how much is it going to float? how much of that log is going to be above the water and how much is going to be below the water. Well, we know that it's going to reach this equilibrium when these two numbers are the same, when the weight of water is equal to the weight of the um, log. Or another way of saying is the mass of water displaced is equal to the mass of the log. So I know that the mass of the log is 1,200 kilograms. So that means the mass of the fluid should also be 1,200 kilograms. But since the volume, or not the volume, the density of the fluid doesn't change, that means the volume of the liquid has to change. So when we do this, we end up getting that the volume displaced actually ends up being 1.2 meters cubed. So that's how much water, or how much of the log is going to be underneath the water. So going back to this, if we actually take this number, so our original volume was 2 meters cubed. So if we take that and we find the ratio of the volumes, so if you recall, this was our definition. When it's floating, this is true. We move the fluid density over, we move this log volume over. We take the displaced volume of 1.2, divide it by the actual volume of the log of 2, we end up getting that it's equal to 0.6, which is the specific gravity. So we end up finding out that the log is 60% submerged. As I said before, the specific gravity has a really interesting relationship when it comes to buoyancy. And this is pretty much it. That whatever the specific gravity of the material is, if you times it by 100, you figure out how much of that material is submerged. So like I said, this is why icebergs always have the same percentage of their volume underwater, because their specific gravity is a very specific amount. I'm going to look it up right now to figure out what the actual specific gravity of ice is. Yeah, so ice has a specific gravity of 0.92, which means that ice will always have 92% of its mass, or 92% of its volume, submerged under the water. So icebergs always have about 92% of its volume under the water. All right? I was close before when I said 80 to 90. Now, the stuff that we just talked about before were basically stationary fluids. Now we're going to move on to allowing for fluids to move. So the first thing that we want to talk about is flow rate. So when fluids start moving, there are two different scenarios that can happen. The first one is a streamline or a laminar flow. Now what this means is basically that when the fluid flows, all the particles are basically very neatly layered. You end up getting this nice and organized flow. If you have so this diagram here is a wing within an air tunnel. So you can see the air just neatly going over it, coming in and underneath, as opposed to a turbulent flow. Now, turbulent flow happens when the fluid starts to kind of overlap itself, and you end up getting a very chaotic result. So if you take this and you increase the angle too much, you end up getting this, chaotic stuff going on over here. So this is a turbulent flow. It's usually why planes tend to start to vibrate when they start to feel turbulence. Basically, it's saying that the air isn't moving in a nice, organized way. Now, when we're talking about a moving fluid, what we're going to talk about is the flow rate of the fluid, or how much mass is actually moving. So, sorry. So we have the mass flow rate is the change in the mass over the change in time. Now, the thing is, again, when it comes to liquids, we can't talk about mass, so we have to replace mass with rho v. So the change in the mass is equal to rho times the change in volume. Just like before, we take volume and we're going to replace it with the cross-sectional area times some increment of length. So we're going to replace volume with A times the change in length. And then we can simplify this a little bit more and say that the change in the length over the change in time is just speed. So the flow rate, the mass flow rate of the liquid is going to be equal to its density times its area, cross-sectional area, times the speed it's moving at. Now, the important thing is that the mass flow rate is the same. The amount of material that's going to flow through here has to be the same over here. So that means this relationship of rho AV is the same on one end of the tube as it is on the other. But since we're talking about a continuous liquid, its density isn't changing, so we can cross these out to get AV equals AV. This formula is usually known as an equation of continuity. These are some other names like transport equation or principal detail balance. Basically, it's the idea that this relationship always remains the same. Now, if you note, this is actually very similar to current flow rate or charge flow rate, where if you remember, if you've taken electrostatics or electricity, and you've talked about circuits, one of the things you know is that like the current coming into a circuit is equal to current coming out. Doesn't matter, how many wires you have, doesn't matter how many resistors you have, the current's always the same. It's kind of that same idea. All right, so what we're gonna have is this. We're gonna try this problem and see how it relates to blood moving through veins. So pause the video, try this question out yourself, and we'll go over it in a second. All right, so we know that AV has to equal AV. All right, now the thing is, on one end we have the area. We're going to use the cross-sectional area of one of the arteries. So the blood goes from the arteries into the capillaries. So one area is going to be the arteries, the cross-sectional area. So we know what the radius is. You know what? We probably should convert everything into the same units since this is in meters per second. Yeah. But over here, what we're going to have is we're going to have the same thing. This will be the cross-sectional area of the capillaries. Now, the one important thing is that the blood isn't going through just one capillary. It's going through multiple capillaries. And we're actually trying to figure out what that number is. So what we're going to say is it's going to be N times the area of one capillary. So if we move these terms over to the other side, we end up getting this. The pi's drop out, so it simplifies to being r squared v for the aorta over r squared v for the capillary. Getting all the units the same, so I'm putting them all into centimeters here, so I'm just going to take this, put into centimeters per second. We end up getting that the number of capillaries is going to be somewhere on the order of 10 to the 9th. All right. One thing to know is if you ever see this phrase of estimate something, it usually just means that we're not caring about the number, we're actually caring about this point here. So if you gave me 10 to the 9th or 10 to the 10th, both of those would probably be accepted. And no usual units either. All right. So here's another question about flow rate. You'll have to play around with the numbers. You'll have to kind of do almost unit analysis. Think about what variables you have on both sides. So you can pause the video, practice yourself, and we'll go over it in a second. All right. So again, we start off with the same term, AV equals AV. Now we know what the speed of the air is in the duct. We know we're looking for the area. So that means we should have enough information to find this stuff. Now, the interesting thing here is that they give us volume of the room, and they give us the time it takes for the air to be replenished. Now, at first, it may not seem like we have these things because, how are you going to find the volume if you don't know the cross-section area of this or the length? But if we kind of take a step back and look at our previous derivation of this, what we can do is actually backtrack and say, well, remember, velocity is just length divided by time, and area times length is volume. This was actually from what we said before when we were doing our derivation on the mass flow rate. So we take this, we're solving for A1, we move V1 over to the other side, and now we can plug our numbers in. Again, we have to get our units all the same, so we have to get this 15 minutes into seconds, and we get that the area of the vent needs to be 0.11 meters squared. So this is actually something that people who end up doing HVAC need to be able to do, is know about, well, what area is needed in certain pipes in order to get a replenishing rate, if you will, in a room. So yeah, they may not do this exact math every time. They might have a way of simplifying it where they might know, the speed's always 3, so they just know which areas relate to the replenishing rate of certain sizes. But yeah, this is actually something that is used very regularly. All right, I'm sure everyone's probably wondered at one point, well, how do planes fly and how do sailboats move? Now, one way to think about it is just a bunch of magic. But as we know, that's not true. It's all science. Magic is just science that people don't know how to explain. So what we're going to use is Bernoulli's equation, which basically shows that there's a relationship between pressure and velocity. And that, in fact, it's an inverse relationship, that when the velocity is high, the pressure is low, and vice versa. So what we're going to do is we're going to derive Bernoulli's equation by considering a pipe. Liquid is flowing through the pipe, and the pipe, just so that we get a bunch of scenarios, has a height difference. So it's going from a low end up into the height, and it's also changing its size. Now on this end, there is a pressure being exerted onto it. That's what's actually pushing it up here. So that pressure is going to actually give us some amount of work that's being applied to the water. Work is just force times distance, so we can replace force with pressure times area. So that's our first equation. Now we can say the same thing, that there's going to be another type of pressure on this end that's actually going to be pushing back against this. So we're going to actually give it a negative PAL. Now there's a third type of work, which is that we have to fight against, is the work done by gravity. So as this water is pushed up, we're fighting the potential energy. So we're going to have minus mgh here, the change in the heights. Now the total work being applied to this is just the sum of these three terms. So we end up getting this when we combine them all together. Now, the work done on this tube is going to be equal to the change in the kinetic energy of the water at this end versus this end. So what we're going to do is we're going to take this entire term that we just found and set it equal to the change in kinetic energy. So we're going to move some things around. Like, for example, we're going to replace this, like this area and length, we're going to replace that with volume. So this is V1 and V2. And we're going to basically, divide every term by volume, and then wherever we see mass and over volume, we replace with density. So that's where this is simplifying to. So this is our pressure differences. This is the potential energy. This is from the potential energy. And this is the kinetic energy part. Now what we're going to do is take all the terms from this side, move it over to the left, take all the second-hand terms, put to the right, and we get this. So this is actually Bernoulli's equation. P1 plus 1/2 of rho V1 squared plus rho G Y1 equals the same thing. So the idea is that this relationship remains constant throughout this pipe. Now, to make life easy, a lot of times some of these terms may end up crossing out. Like, for example, you might have a situation where both ends of the pipe are exposed to the same air pressure. So the P1 and P2 can drop. Sometimes you might have a situation where the pipe remains level the entire time, which would take this third term out on both sides. But basically, you're going to end up playing around with this. This is your general fluid motion equation. All right, so try using that equation for this. Pause the video, work on it by yourself, and we'll go over it in a second. All right, so we're going to take, first we have to use AV equals AV because one thing is that we need to figure out what the flow speed is on the other end of the pipe. We know that the pipe changes its diameter. It goes from 4 centimeters to 2.6 centimeters, and we know its initial speed. So we're going to use that to figure out what its new speed is. Again, we do area of a circle because that's a cross section of the pipe. Plug the numbers in. I actually don't need to convert the 2.6 and the 4 because they're both in centimeters, and it's just going to cross out. So I end up getting that the flow rate speed on the other end of the pipe is 1.2 meters per second. To figure out the pressure on that end of the pipe, I'm just going to use Bernoulli's. So I have everything. I know that this is 3 atmospheres, though I need to make sure that all my units are consistent. So I'm going to have to convert that 3 atmospheres into pascals. So I take that, I put in my speeds that I just found before, I put in the height difference, making sure you use the density of water, and end up getting that the other end of the pipe has to have a pressure of 2.5 pascals. I don't want it in pascals, so I'm going to convert it into 2.5 atmospheres. Now, because it didn't explicitly state that I wanted the pressure in atmospheres, on a test or on homework, I would have accepted either one of these answers. Normally you do want to try to keep an eye out for, though, is what unit is being, that they explicitly want your numbers in. All right, so there's actually a bunch of different applications with Bernoulli's. You're going to see a few examples in the homework, but one common one is called Torricelli's theorem. Now, I do want to point out one thing. I said before that you do not need to show on a test a derivation. What I mean by that is this Bernoulli's equation is a very general equation. This is something that you do not need to show me how you derive it. You could just say it's true and I'll believe it. Torricelli's theorem, on the other hand, is a very specific application of Bernoulli's. It's not a general equation, it's a specific equation. So if you're doing a problem, you cannot straight use Torricelli's theorem. You would have to actually use Bernoulli's to get and then show how you get Torricelli's, because you never know. Then a situation, while it may seem very similar to Torricelli's situation, might be different enough where the equation doesn't work. Again, you're going to see that in the homework where you'll see a few examples that look very similar but have slight differences. So with Torricelli's theorem, what we're doing is we're going to look at a vat, and at the bottom of the vat is a little spigot. And we want to know, well, what is the velocity exiting this spigot? And we're going to assume that the velocity at the top is 0. Again, that's the big thing. With Torricelli's theorem, we're assuming that the velocity is 0. Now, since both the top of the vat and the spigot are being exposed to the same pressure, air pressure, we know that the P's are going to drop out. So Bernoulli's equation simplifies to this relationship. Now, I can simplify it even further by getting rid of all the density terms, because it's all water, so why even have it? I can also say that V2 is 0, so this term is going to drop out, and I get this. I can move some things around, and I'm solving for V1, and I'll end up getting rad 2GH, essentially, which is pretty interesting because I'm pretty sure that's exactly the relationship you would get when doing any object falling from a height, and you're trying to figure out its speed. You end up getting rad 2GH. So we can use we can go back to what we were saying before about how Bernoulli's explains boats and planes, and when we look at it, it makes sense. So planes fly because there's going to be a difference in pressure from the top and the bottom. Now, in order to lift up, the pressure down here has to be higher than the pressure up here. Well, according to Bernoulli's, there's an inverse relationship between pressure and velocity. So the lower the pressure, the higher the speed. So wings are designed so that the speed of the air is much faster up here than it is down here. Like I said, also the last sentence in this paragraph basically says that we also need to make sure when we design wings that we maintain a laminar flow. There's no point in getting the speed to be faster up top if it then becomes chaotic and ends up causing excess pressure and forces on our wing and breaks it. Boats are also able to move against the wind by doing kind of the same idea that the faster speed on one end will result in a lower pressure and push the boat in that direction. All right, so this is some excess stuff that you don't need to worry too much about. So the first one is about viscosity. So viscosity is something that we haven't talked about, but it's actually a natural internal friction that occurs within a liquid. The unit that we use, or the symbol that we use for viscosity, is this eta symbol. I forgot what the name of it is. So one way to think about it is, you have a moving plate, and if you pull it with some force, it's going to move at a constant velocity because the liquid underneath is going to kind of pull it back a little bit. And you end up getting a velocity gradient that moves all the liquid underneath it. So one way of thinking viscosity, as we all probably know, like I said, from what living and existing in the world, is its resistance to flow. Objects that have a high viscosity tend to flow a lot slower. So things like honey, or I can't remember another syrup, have a very high viscosity, while something like water or ethyl alcohol will actually run a lot faster. So the viscosity of honey is higher, it's going to flow slower than water. Now the equation we can actually get an equation for the viscosity by actually considering this of like, well, what force would be needed so that the plate moves at a constant speed is actually given by this this viscosity, which can be reworked to be viscosity is the force times the length between the two plates, between one surface and the stationary surface, over the area times velocity. All right. Now, the viscosity also actually is temperature dependent, but you don't need to worry about that. But that does kind of make sense. As we know, when you increase the temperature of something, the speed of the molecules will increase, so it will allow for a much easier motion. So the viscosity based off of temperature will actually decrease as we increase the temperature. Interesting note though, there are some materials that when we actually get super cold, its viscosity goes down. In fact, superfluid helium is one such example that when it goes to a superfluid state, about 3 degrees away from absolute zero, it ends up having going to a state where it has zero viscosity. All right, we can then take viscosity and flow rate and Bernoulli's and combine it all into an equation called Poisson's equation to talk about blood flow rate and see its relationship to radius of the veins. We have an equation for the flow rate as being equal to this. So here's our viscosity, the pressure difference, and this is the radius of the capillary. Now, one interesting thing about this, which is why I want to talk about it, is that because of the very high power, the power to the fourth on that radius, it basically shows that even the smallest increase in your radius is going to result in a significant decrease in the flow rate. So this basically shows that why clogged arteries is so important. So it says here that if the radius is cut by half, then the flow rate ends up decreasing by a factor of 16. So yikes. Very important to make sure to keep those arteries clear. We have another thing. Like I said, this is some extra stuff. I'm going to briefly go through this. So this is surface tension. So as you know, liquids have a bond that that connect them. So this actually means that they have a surface that requires a certain amount of force before it can actually break that surface. For most materials, it's not really that high. We call this surface tension, and that gamma is referring to the surface tension. This is pretty much how you get if you remember that scenario where you make little droplets of water on a penny, see how many drops you could put on it before it spills over. It's that same idea. Now, there's actually an animal called a water strider that is actually able to walk on water. Essentially, it's able to distribute its weight in such a way that it doesn't break the surface tension, even though its weight technically would. You can actually see it here. It's pretty cool. It kind of almost looks like it's on a trampoline. Like you could see it deforming the surface, but not actually breaking. So the equation that we have is that the surface tension is equal to the force being applied divided by the length it's applied over. So typically, if you want to be able to have the surface tension withstand more force, you need to displace that force over a much greater length. One thing to note, never mind. Going back to here, what we have is a question with the water strider. If you want, you can practice yourself, or you could just wait for me to go over it in a second. All right, so I'm just gonna go over this. So it wants to know what angle do the legs make. So like I said, the way that the water strider works is by distributing its weight over a large area. So the angle will actually result in two forces of the surface tension pushing up at these angles while the weight is pulling it down still. Now the vertical component of these forces is actually what's counterbalancing the weight. and the length that it's over is going to be the circumference of the circle. So what we're saying is this is actually kind of the whole the y component, if you will, times the of the surface tension times by the length. Plugging the numbers in, since it has 6 legs, we're just going to say that the weight of it, the Fy, is 1/6 of its overall weight for each leg. Plugging the numbers in, solving for theta, we end up getting about 57 degrees. So in order for the water strider to be able to stand on the water, its legs have to make an angle of about 57 degrees to the vertical. Now, we did ignore buoyancy force, but for simplicity. All right, we also know that this surface tension actually also kind of results in 2 scenarios of cohesion and adhesion. So cohesion is a scenario where the liquid actually ends up being more attracted to itself. You end up getting what will result is that the material will actually almost bubble up and try to make it so that it has as little surface contact with the surface as much as possible. A good example of something that has a very high cohesion is mercury, as opposed to water, which does the opposite. It has very high adhesion, meaning that it's much more sticky to the object than it is to itself. Yeah, I don't know why the word attracted got cut out. So this is actually where, like, when you look at tubes, why there's that thing called the meniscus, where it kind of goes to its lowest point. That's the reason, because water is more likely to attract to other objects than itself. This is just another example of, like I said, capillary action. Mercury would rather touch itself than touch the surface. So water is more likely to go up in a tube, while mercury would want to stay low. All right, so these were some of the equations we talked about. Again, the biggest things were being the pressure. You want to kind of keep an eye out for, when you're doing the problems, keep an eye out for the wording that they use when they want you to find absolute pressure, and the wording that they want you to use when they find gauge pressure. It's extremely important. We also have the buoyancy equation, the Archimedes principle, we have the flow rate equation, and then we also have sorry, not Archimedes. Yeah, the Archimedes principle, Bernoulli's equation. And then from Bernoulli's, the whole idea that the faster the flow rate, the lower the pressure. So these questions are going to be due on Monday. This is chapter 13. So we have these 10 questions, a little bit evenly spaced out compared to the other ones. So all these are things that you're going to want to make sure you know how to do. All right, so that's it for this video. The next video that I'm going to show is a kind of a recap of all the extra problems that are after this, so you can work on them yourself. Otherwise, see you in the next one.